Hello again, everyone, wherever and whenever you're watching this video. A few small bits of bookkeeping today. I had not posted a video for yesterday. In that particular case, there was a situation where there was a storm coming through St. John's, and I wanted to give the people who were still there some time to focus on snow clearing and friends and family in, of course, what are very difficult times. So that explains why there was no video yesterday or daily assignment, to really give you all a bit of a break to spend some time focusing on some other things, because obviously there's stuff that needs to be done. But now we're going to get back into it. We're going to get back in at the point where we left our last video. And so we will effectively be looking at what we've learned about gases in terms of pressure. We would have seen in the last video that we are essentially often using the idea of liquid pressure to help us figure out gas pressures, or we're really trying to build up to that. We see that the pressure of the air around us is really the weight of about 120 kilometers of air being pulled down under the force of gravity, stacked right on top of our heads. And that means that, evolutionarily, we've kind of, grown with that idea, so we don't feel it, but it's there. But when you get more weight pressing down on you, like we've said before, as you swim down to the bottom of a swimming pool, there's that weight of the water pressing down on you. And we would have seen that by using weight of liquid, we can effectively figure out the weight of air. And that means we can really take that weight and apply it over a certain area. That tells us a pressure. And now we know the air pressure. And we can probably use a lot of the same ideas, as we're going to see in a few slides, to measure pressures of samples of gas in that particular case. But before we get there, let's focus a little bit on the idea of units of pressure. We've seen that many of the units that we have in our world are for the same kind of measurement ideas. So the imperial units of feet and inches and yards for measuring distances, where we now use meters, centimeters, decimeters, and things like that. It's still the same idea. And we've seen very early in this course that we have to be able to convert from one set of units to another. They're really telling us the same information, but how we're kind of grouping some of that information in chunks is different in size, really. And that's why we have to account for that. So pressure, it turns out, can be measured in many, many different units. There's one of my favorite kind of historical units, again, for car tires, bike tires, anything like that, is pounds per square inch. Pounds, a weight, a force per square inch. That's a unit area. So that really does fit the idea of the units of pressure being related to force or weight divided by the surface area. We've seen that weight could be 760 millimeters of mercury, essentially pushing down on you. And so that led us to a unit of pressure called the millimeter of mercury, which we found out was very equivalent to a torr, pretty close to about 4 decimal places, in fact. And so what we can find is there's other units of pressure that you might see out in the world there. 1 atmosphere is a pressure of 1 atmosphere. What kind of normally the air pressing down on us kind of weighs. And, of course, with weather, that changes. That's the idea of barometric pressure rising and barometric pressure lowering, which we often associate with changes in the weather and things like that. But yeah, on average, you can say the air pushes down on us a certain amount. That's 1 atmosphere, because that's our atmosphere of the planet Earth. Well, that atmosphere has to be the same as the pressure exerted by a column of 760 millimeters of mercury, because we saw that when we actually create the barometer by tipping that tube of mercury into a pool of mercury, and essentially the air pushing down on one side supports the weight of 760 millimeters of mercury on the other side. And so we saw that 1 atmosphere, that weight of the air pressing down, has to equal that 760 millimeters of mercury, or 760 torr. So there's another one of our unit conversions to work with. But we're, of course, metric. And science, for the most part, again, System International, metric prefixes, and so on, which means we're going to want to connect things to the standard units that we have. Now, we saw the standard unit pressure, or the System International unit of pressure, is the Pascal. I would have said at the time in that video that the Pascal is a very, very, very small unit of pressure. It turns out, in fact, that if we want to consider the pressure of the atmosphere, 1 atmosphere in those kind of older imperial units, we're going to find out that that's 101,325 Pascal, which is 101.325 kilopascal. So when you're reading the Weather Network web page or something, or watching the weather, and they start telling you again about the barometric pressure rising and falling, they might say that it's 101.28 and rising. Well, that would be 101.28 kilopascals in that particular case. Another thing I want to mention, especially about this last set of conversion factors, is that we have these defined as being exact. So in other words, these conversion factors, we're never going to worry about sig figs when we use these. It's always the piece of data that we're converting that will help us determine the sig figs, but not any of this. So just because I see 6 sig figs on one side and what appears to be 1 on the other side, no, you can have as many as you want when you're doing that conversion from atmosphere to Pascal or kilopascals. Now, some textbooks, a lot of chemistry textbooks, in fact, will use 1 atmosphere as the standard of pressure. And why shouldn't it be? Because it is the kind of average pressure of the air around us at any given time. The thing is, the atmosphere, as we've seen, is connected to the idea of 760 millimeters of mercury and things like that. And that's just not kind of the System International way. It's not really metric in how we use it. So what we have to do is we have to use our standard or System International unit of pressure to help define what we're going to call a standard unit of pressure, at least in a scientific context. The reason most textbooks still use 1 atmosphere is because most textbooks are American, where they still treat pressure and a lot of other things in imperial units, even in science, because that's, of course, when you move into university after having gone through elementary school, junior high, high school, that's the system of measurement that they've used their whole lives down in America. We are, delivering this content in Canada. Our textbook, Chemistry and Molecular Approach by Trove, Fridgen and Shaw, Dr. Travis Fridgen, our Associate Dean, undergraduate in the Dean of Science office, and a colleague of mine in the Department of Chemistry. That's the Travis Fridgen of the textbook. One of the things he did to make that textbook a Canadian edition was essentially take every problem in there and really convert them to standard units or System International units. So where all the questions used to ask things in terms of atmospheres, they might read in bar or Pascal, because that's, of course, what Canadian students have seen. But that's really the units of science for the most part in most of the world. Now, so the standard unit of pressure we're going to define as 1 bar. It's standard, so it makes sense to just kind of label it as 1. It's this big thing, just like 1 atmosphere, but 1 bar, we're going to want to have to connect that to the System International unit of Pascal, and if it's System International, we want it to be really a power of 10 magnitude, a metric prefix. So 1 bar turns out to be 100,000 or 10 to the 5 Pascal, and that's exact. Or 1 bar would effectively be 100 kilopascals, is what we would find in that particular case. Now, it turns out a bar is slightly smaller than an atmosphere. It's 0.98692 atmospheres, in fact. And so you'll notice I've got this kind of approximate symbol. Really what we're saying is, yeah, there's really about 5 sig figs in that conversion factor. So this one is not an exact conversion factor in this case. But here we see table 5.1 from the textbook. Here it's showing us some common units of pressure. There's that pounds per square inch right at the bottom. And so what we find is, yep, the standard pressure is 1 bar. That's what we're really comparing everything against, just like the idea a dozen is 12. That's the comparison that we're making. So in pascals, that's 100,000 pascals, or 100 kilopascals. Turns out to be about 750.1. I think it says 0.01 here. I think it's 0.1. That may be a little typo. We've got torr, or millimeter of mercury. It's 0.98692 atmospheres, and there's that pounds per square inch, 14.504 pounds per square inch. So if you're filling your car tire or checking the pressure in your car tire, you're going to see that the tire manufacturer probably wants that tire pressure about 30 psi. In other words, there's really about twice as much pressure inside your tire as outside, and that's of course why your tire balloons out, even though it's usually made of some fairly stiff rubber. It is effectively a balloon with very, very robust sides, unlike, let's say, a mylar or latex balloon for a birthday party. So this leads into our idea that we can measure the pressure of a sample of gas by effectively using the same idea as the barometer, but what we're going to do is something slightly different. If we look at the picture on the right-hand side, which describes a piece of equipment called a manometer, so of course we're measuring something, and really what we're going to be measuring is the pressure of a gas here. And what we're going to see is that we have some similarities to the barometer in that we've got mercury liquid, and we're really going to be using a column, a height of mercury to help us figure out part of the equivalent pressure of the gas inside a sample. Now, in a barometer, what we would have found is we would have had a closed tube here, our pool of mercury, or down here, and we invert the tube there, and of course mercury would run out until the atmospheric pressure on one side, essentially the open side of the pool of mercury, would match the pressure of the weight of mercury in the tube, and that was how we could measure the barometric pressure. Here we're doing something slightly different. Really here we're seeing the pool, or the kind of idea of the pool, is actually replaced by this open end of the tube. This is where the air is pressing down. So this is effectively the same idea as the air outside of the closed tube in the barometer pressing down. So this would be the equivalent of the tube, but where we inverted the tube of mercury in a barometer into a pool of mercury and some ran out, there was nothing left in that headspace. That was a vacuum. There was nothing there. Here, it's the same idea. We've really got a tube that doesn't have mercury in it, but where there's not a vacuum, what we have is gas on this side from our sample here. So, in the barometer, there's nothing pushing this side down. Really, the only thing pushing this side down effectively is the weight of mercury that would be matched by the atmospheric pressure. Here, there is something pushing down, and so really what it's doing is pushing up against the atmosphere. And because of that, we can now measure this pressure inside if we know this pressure outside, because it turns out that there still has to be a balance. The pressure of the air on this side, the weight of the air pressing down on a surface area on this side, plus the weight of the mercury difference in height between the two sides, that's the extra weight pushing down on this side, well, that's two weights over surface area. That's two pressures. Those two pressures would have to balance out the pressure inside, because if this isn't moving, there is balance in that particular case. So what we're going to find is the pressure of the gas inside this bulb is going to equal the pressure of the air, the barometric pressure on the outside, plus an additional pressure that depends on this height of mercury and whether it's higher on the open side or higher on the closed side. Because if it's higher on the open side, that's extra weight on the open side that's needed to balance the extra weight or pressure coming from the other side. If this height were reversed and we saw a column of mercury up here and more air here, then what we'd be saying is the pressure here plus the extra weight of mercury would have to balance what's happening down on the other side. And so, of course, this height, well, that's a height of mercury, which is given in, let's say, distance units like millimeters, which means that change in height or that difference in height is in millimeters of mercury, which means it's already in a unit of pressure. That can become a little more obvious when we work on this problem. So this problem says, let's say we've got a mercury manometer, like we just saw in that previous picture. We're going to find out that when we put a sample of gas into our, whoops, wrong one. If we put a sample of gas into our bulb on the closed side, we're going to see that, yeah, there's going to be a height of mercury on one side or the other side. In this case, we're saying the height of mercury on the open arm is 7.83 millimeters higher than in the closed arm. So that's that idea that if we have more mercury, or the height is higher on the open arm side, that's the extra weight of mercury that's required to add to the weight of air or pressure of air to balance what's happening inside our bulb. So that's extra above the barometric pressure. In other words, what's happening inside the bulb, if we were to poke a hole in the bulb, the pressure in the bulb would be higher inside than outside, and we would have gas rushing out, what you would expect if you pop a balloon, for example. So here we see that if the pressure barometric is 748.2 millimeters of mercury, then what is the pressure of the gas in the manometer? That is that idea that we have seen in our equation on the previous slide, that the pressure of the gas equals the pressure barometric plus the change in pressure, which is really, if we have a weight of mercury or height of mercury, well, we've seen, again, that can be a pressure. And we've effectively seen that this would be P barometric plus the height in the open arm minus the height in the closed arm. And so that would be effectively the 748.2 millimeters of mercury, plus we saw the height in the open arm was higher. In other words, we'd expect this change in height, this delta height, to be a positive number. That positive number is going to be 7.83 millimeters. And millimeters of what? Millimeters of mercury. So yeah, let's get my handy-dandy calculator out. Just give me a moment while I do that. You'll notice that I'm trying a little experiment where I'm trying to put some closed captioning in these videos. As universities for the spring and summer semesters are transitioning into remote-only learning, at least that seems to be what's happening in a large number of places, obviously figuring out ways to make content like this lecture video accessible to those who have exceptionalities in their hearing or other sensory situations. Obviously, finding ways to help my lecture videos be as accessible to everyone as possible is certainly something that I'm very interested and happy to explore, because of course, if I, well, actually more when I figure out where I'm teaching in the summer, obviously these are the kind of technologies I'm still going to be using due to the current situation we find ourselves in. So like closed captioning, it's really relying on the same kind of voice recognition technologies as Siri and Alexa and all those things. And as we all know, when we have tried to dictate a text to our phone, that sometimes it doesn't do a very good job. So please don't be surprised if the captions if you're using them, are not perfect. It's the same kind of thing that you sometimes see when you're watching the closed caption on the television. They're going straight speech to text recognition, and if you're someone like me who can sometimes mumble, stutter over his words, or just plain mispronounce them, just like I mispronounced the word mispronounced just now, then you're going to find that, yeah, they're not always going to say exactly on the screen what was said in terms of the sound. But in terms of at least giving people another option for how they take in what I'm saying, I think it's a great thing, and that's why I'm trying it. So in all that time, that was effectively me trying to buy time while I did the math, and then I spent a whole lot more time talking about what I'm doing there. But yeah, what we're going to find, 756.0 millimeters of mercury. Again, while there are 2 decimal places in that height of mercury, there's only 1 in that barometric pressure, and so we can only have 1 decimal place when we add those together. That 756 millimeters of mercury is really telling us that the pressure of the sample of gas we have is slightly less than what we would think of normal atmosphere, slightly more than what we would think of normal atmospheric pressure, because that would be about no, still slightly less. See, making mistakes. I'm actually recording this at 11:30 in the evening. That's just how things worked out today. So I'm a little tired at this point, but I'm going to get through it because we have about 20 minutes left. We're going to get this done. We're going to learn some good stuff. So 756.0 millimeters of mercury. The atmosphere is 760 millimeters of mercury. So what we see is, yeah, this is pretty close to a balloon, really, effectively, because a balloon would have to have the same pressure inside as outside, or we'd see the balloon get bigger and smaller. That's actually one of the things we're going to talk about very soon, the idea of gas laws and how if we make a change to one of our variables that we use to describe our gas and hold 2 of the others firm and constant, then the last variable has to change to accommodate what we've done. So let's see where we get to next. Aha, here we are. So the first of those simple gas laws, Boyle's law. Now, a lot of stuff happening here for a fixed amount of gas at a constant temperature. Again, I said, look, we've got those 4 state variables of gases. We have 4 things that we need to know if we fully want to describe a gas. But if we change one of those things, the other things are potentially going to change, because the whole idea is that really this gas wants to have some sort of fixed behavior at a fixed set of conditions. Once I know these 4 things, that always looks the same for that sample of gas, no matter where it is, no matter when it is. So we need to simplify things, though. If we've got 4 variables, each of which could change when I make a change to any of the others, we need to essentially lock things down, put constraints on things, so we have the idea of understanding how if I change one thing, how does this one other thing change? And so that's what we're doing here. I said of those 4 variables, if we hold 2 of them constant, we can see how the other 2 will change when they're essentially looked at as a combination. And so for a fixed amount of gas at a constant temperature, those are the 2 things we are keeping fixed, which means the other 2 variables we're talking about, the gas volume and the gas pressure, are going to have some sort of relationship that when I change one of those, the other one is going to change as well. Now, it turns out that when we take the gas volume multiplied by the gas pressure, that number is always constant for a fixed amount of gas at some given temperature, like let's say 25 degrees Celsius. And this actually matches our idea of what we've experienced in our own lives. Imagine here we've got effectively a gas in a closed tube, closed J tube, with some mercury in it open to the atmosphere. You want to know something very funny? This is really no different than our manometer. But instead of having a bulb at the end, we just capped it off here, but we still have gas in there. So this is really a manometer. It's a very, very crude manometer, but frankly gets the job done. So here's our sample of gas. We see that because of the air pressing down on this side, as well as this extra weight of mercury, or coming down, really height of mercury coming down, then what we're going to see is those two pressures would have to combine to tell us something about the pressure in this part of the tube here. So there's a certain pressure in here, and of course there's a certain volume. We could figure that out fairly easily, assuming the tube is nice and smooth inside and it's a cylinder. We know the geometry to figure out the volume of a cylinder. So we know the volume in there if we know something about our piece of glassware. Now, if I pour some more mercury into the other side of this tube, the open end of the tube, what I've got is a new situation. In that new situation, we're going to see that, of course, I'm pouring extra weight by adding extra mercury. It's like we're going deeper into the swimming pool and there's more water now above us. And what we're going to see is two things happen. First, we're going to see that if we compare the mercury levels, our height of mercury has increased. Well, that shouldn't surprise us. We added more mercury. It had to go somewhere. It's still there. So of course the height is going to go up. It'd be no different than if I pour water into a glass. The height of water goes up as well. But what that higher height on this side means that's extra pressure. Again, that's like going deeper into the swimming pool. More water above you when you're 10 feet down the pool than when you're 3 feet down in the pool. That's in fact 3 times as much water pressing down on you, and you certainly feel that when you're in the deep end at the bottom of the pool. Or even if you're putting your hands in the sink or the bathtub or whatever, you can feel the weight of the water. So yeah, we added pressure. And what we found is the adding of pressure made the volume that the gas occupies smaller. This is Boyle's law, that the two things must multiply together to give us some constant value, which has a dependence on how much stuff we have and the temperature we're at. So of course, if we change the fixed amount of gas or change the constant temperature, this thing that we're going to call A, this constant, is going to change on us. But what we see is this: pressure times volume is constant. If I have a pressure of 1 bar for a gas that occupies 1 liter, very, very simple idea. If I increase the pressure to 2 bar, well, if 1 times 1 equals 1, and that 2 bar of pressure has to be multiplied by something to also give 1, what we find is that volume is now half of what it used to be. 1 times 1 is 1, 2 times 1/2 is 1. And so what we see is that we get a situation that as we increase the pressure, the volume gets smaller. If we double the pressure, the volume will be half. And if we make the pressure 4 times as big, the volume will be 1/4. We see this graphically here in the bottom corner. A graph of the volume of a gas with some amount and some temperature. We don't care. We're more interested in the behavior right now than what those details are for this specific graph. But yeah, the volume versus the pressure. We're seeing how the volume changes when we change the pressure. And what we see is this. At millimeters of mercury, effectively right here would be about 760 millimeters of mercury. And so around there, what we're saying is this particular sample of gas at whatever temperature it's at around 760 millimeters of mercury, possibly has a volume of, let's say, about 22 liters. That's just a number I'm kind of guesstimating by dragging across here and to our axis. And we see it's about 1/4 of the way up, maybe not so much. This is the idea of extrapolating or interpolating data from graphs or reading data from graphs. You essentially find the point you're interested in. You may not have actually taken a measurement at that particular pressure, but it doesn't matter. As long as you see how the change occurs, you can get a very good sense of, by fitting the curve going up and across, you can get a very good sense of what the volume probably would be if you were to make a measurement of that gas sample at that particular pressure. And what we see is this. As we decrease the pressure, as we effectively remove mercury from the tube, what we would see is the volume goes up. And what we see is if we go from about 760, well, half of that is going to be about 380. So a pressure of 380 is here-ish. And what we're going to find is, well, that's closer to halfway between 0 and 100, which means maybe we went from 22 liters to 24 liters. We actually see the data showing this relationship that the pressure times the volume is constant. Well, that's something very interesting then. If the pressure times the volume is constant, and then if I change the pressure, the volume changes to maintain that constant, then that gives us this equation that we can use to solve for any new piece of information, as long as we know the other three. If the pressure in the first situation multiplied by the first situation volume is a constant, then the pressure in the second situation multiplied by the volume in the second situation has to equal the same constant, which means those things are equal. That's that idea again of 1 bar and 1 liter. Well, if I double the weight pressing down, that's doubling the pressure. 2 bar, you'll see that the volume becomes half of what it was, half a liter. And this simple gas law lets us understand how volume changes with pressure. Let's take advantage of what we've just seen and do a problem related to it. And here we go. So let's add another sheet of paper. Let's get our picture of that slide in there. Of course, it would help if I could see these a little better. So I just need to take one quick look at some of the colors. A lot of blue and purple, so a lot of blue and purple would probably be this one. There we go. Took some time, but hey, like I said, a little dozy, doing this pretty late at night. That's just how today worked out. So there we are. We've got our problem. A sample of gas has an initial volume of 5.6 liters at a pressure of 735 torr. If the volume of the gas is increased to 9.4 liters, then what's the pressure of that gas? And here's where we have to be careful, in bar. So we're effectively being asked to do a unit conversion because we're going to be able to solve for a pressure in torr and then convert to bar, what we're asked for, or we're going to have to take that initial pressure of 735 torr and convert it to bar first. Then we can solve the problem, and we would get the answer in bar in that particular case. Doesn't matter which way you do it. At the end of the day, it's order of operations in that particular context of conversion factors doesn't matter. You just want to make sure that you're applying them correctly. And that's, again, where dimensional analysis has been our friend all along. So effectively, of course, this is our Boyle's law question. So we're effectively saying our pressure initially, I'm saying initial instead of one, doesn't matter. It's just some sort of way of identifying one pressure from another. And since we said initial volume and initial pressure, yeah, let's say initial volume and initial pressure. And of course, that means that's going to have to equal the final volume and the final pressure multiplied together. Again, those two things have to be constant. Now, you'll notice we haven't seen any mention of how much gas or the temperature. Here we're saying a sample of gas, so we're going to assume that that amount does not change. It doesn't make much sense to have a sample and then throw half of it away right in the middle of measuring something. So there's that. And it doesn't mention a temperature, and in that case, that's when you get to assume, yeah, that's probably not important for what we're trying to do. So that must be the other thing being held constant. So I could have just as easily said in the problem, a sample of gas at some given temperature even though I actually didn't give it to you, or some known temperature has an initial volume, and we be right the same place. So sometimes you can kind of assume from missing pieces of information, especially if you understand the context of what's happening. Boyle's law, looking at how gases and their variables change. When we change one, how does another change? By holding the other two constant. So what we're going to see, we want that final pressure. Well, that's going to be the initial pressure, and we see really how Boyle's law is going to work for us. It's telling us that we're taking the initial pressure and we're essentially scaling it by the ratio of the initial volume divided by the final volume. If the initial volume was bigger than the final volume, giving us the idea that we have squeezed the gas into a smaller volume, then what we would expect by squeezing the gas into a smaller volume, the pressure is going to go up. Alternatively, of course, if our initial volume is smaller than the final volume, effectively the thing got bigger, like blowing up a balloon, but obviously not in this case because blowing up a balloon would be changing the amount of gas, and that doesn't apply in this problem. But the same kind of idea, you can imagine that, well, if I blow up a balloon, the pressure could be larger depending on the other situation. So this means I can throw in, I'm going to do this in torr first and then do my unit conversion at the end. Again, if you wanted to convert the 735 torr right now, you could do it. Again, order of operation doesn't matter. Find the way that you feel most comfortable with, the way that makes sense most to you. And yeah, so we saw the initial volume, 5.6 liters, while our final volume is 9.4 liters. The volume of gas, the problem tells us it increased. So that's really helping us out. So if the volume increased, that should be the sense that the pressure must have gone down. And we can see by the volume ratio, that's going to be a number less than 1. Yet that has gone down. Of course, a good thing about this is we see, of course, the units of liters cancel out because by doing it as a ratio, that should happen. And the only units we have left are, of course, torr, which are pressure units. That is exactly what we want. We've got 735 multiplied by 5.6 divided by 9.4. So let's see where that takes us. 735 times 5.6 divided by 9.4. That is 438 torr, really 4.3 sub 8 times 10 to the 2 torr. 2 significant digits because there's only 2 in each of those volumes. So we can only have 2 in that final number, but I'm going to keep the guard digit because let's do our conversion. We want this in bar. We would have seen that 1 bar in table 5.1. Again, table 5.1 says 750.01 torr. I do believe it's actually 750.1. I think in the 3rd edition of the textbook that has been corrected, but this slide may have used the 2nd edition picture. So I'm going to say 750.1. Do a little internet searching. It might be actually 750.06. That's the wrong units down there, though. Oops, those got to be torr. Because if I do that, of course, my torr units cancel out, leaving me with units of bar. And what we're going to find is that, yeah, I will take my 438-ish. Really, it's actually 437.87. That would be more guard digits, not really useful. But yeah, I'm going to divide that by 750.1. And that is going to give me, to the 2 sig figs I'm allowed, 0.58 bar. Now, does this make sense? Well, we went from about 5 liters to about 10 liters. It wasn't exactly 5 to 10, but hey, it's about half. The initial volume is about half of the final volume. And therefore, if the initial pressure is 735 torr, well, 750 torr is 1 bar, so we're about 1/2 of 1 bar. Well, 0.58, that seems about right. I'm feeling pretty good about that. So this is where we've finished our problem for Boyle's Law. According to my watch, I've got a few minutes left, but you know what? Nothing says these videos have to be exactly 50 minutes. I think we've got some time again without the final exam. I really want you to keep working on your toolkit stuff, because you see, here we are again, unit conversions coming out at us, even in these chapters as we move on. So those going on into 1050 and 1051, this is the kind of stuff that you're building your tool set for. So that means I'll shut down this video for today. Check out your daily assignment in Mastering Chemistry. This will be the last pre-recorded video for this week. A new one with a new daily assignment will show up on Monday. I am currently working on that second chance midterm. That will go up at some point. It will have a due date of April 9th, so there will be time for you to get your opportunities in for that one. I hope, again, safe, comfortable, friends and family are safe and comfortable, and all the best in what is hopefully the last stormy bit of the season for those of you, especially in Newfoundland and Labrador. Obviously, those of you who are further afield back home, I hope you got there safe. I hope everything's going well there. And we will see you all very soon.